In the previous video, we defined ideal quotient of two ideals in a ring. So let us now see an example of this. Let's calculate the ideal quotient of two ideals I and j in our familiar ring of integers. Because we know that this is a Euclidean ring, so every ideal would be a principal ideal. So I and j are also principal ideals. So each one of them will be generated by a single integer, and say the generators are respectively m and n, where it's also given that m and n have these prime factorizations. M is the product of some primes where the exponent of p is mu p, and n is the product of some primes where the exponent of p is nu p. Now looking at the notation, you may get confused at first. It is not given over which set this p is varying. So what should you think of this p? You actually know the answer, because in the prime factorization of a single integer, only finitely many primes appear in a non-trivial way. For example, in the prime factorization of 12, 2 and 3 appear in a non-trivial way. 2 appears in the power 2 square. 3 appears as just 3 to the first power. Strictly speaking, the other primes are also there. For example, in the prime factorization of 12, 5 is actually also there, but the exponent there is 0. So it is appearing in the prime factorization as a trivial prime in this sense. In that sense, you have to interpret this product, thinking of p as varying over the entire set of prime numbers, but with the understanding that at most finitely many mu p's are positive integers and the others are all equal to 0. And that actually also brings a kind of uniformity in these prime factorizations, because it's not necessary that whatever primes you have here, for example, appearing non-trivially will be precisely the primes that appear here non-trivially. That's not necessary. But this way, all primes are taken into account, whether trivial or non-trivial, in a given factorization, all of them at once. Alright, so with all these things, now the claim is that the ideal quotient of I and j is, it's again an ideal, so it will also be a principal ideal generated by q, where q is this integer which has this prime factorization. This time the exponent of the prime p is gamma p. But what is gamma p? Gamma p is the maximum of mu p minus nu p and 0, which also turns out to be equal to mu p minus minimum of mu p and nu p. To see why this is equal to this is very easy, in fact. You just have to consider two cases. You can do it mentally. And those two cases are, the first one of them is the case where mu p is greater than or equal to nu p. Mu p, that is this thing, is greater than or equal to nu p, so that this difference is a non-negative integer. It is greater than or equal to 0. So what will then what will be the maximum? The maximum will be this, because this is greater than or equal to 0. So in that case, this quantity is mu p minus nu p. In that same case, what happens to this minimum? Because mu p is greater than or equal to nu p, the minimum is nu p. And that's why this is also mu p minus nu p. So they are equal. And the other case, of course, is mu p less than nu p. That I am leaving to you. Okay, so in that case also, you will have this equal to this. And because of this fact, q is equal to m divided by the greatest common divisor of m and n. I am not going too deep into how this follows from this. You will figure out yourself, okay, using a little number theory. So now we have to see how this is true, how all of this is true. So let's see. So what we do, we take an arbitrary element x in the ideal quotient of I and j, and we want to prove that this x belongs to the principal ideal generated by that integer q. So this way this will be a subset of q, and then we will prove the reverse inclusion as well. So then what does it mean? By definition, then xj would be a subset of I, because that's the definition of ideal quotient. That means x times any element in this ideal j would be an element in the ideal I. In particular, if we take x times the generator of j, that is n, that x then would also be an element in I. But what are elements in I? They are multiples of m. So that way xn is some multiple of m for some integer k. Alright, so that means what? If you divide both sides by n, you then get x equals k times m divided by n. Now using the prime factorizations of m and n, we get this. Okay, that is p to the power mu p minus nu p. Here you do not again have to be worried about whether this product is convergent or not, because at a time only finitely many primes are actually involved in both the prime factorizations. So this ratio m divided by n, it's just a ratio, okay. Here also only finitely many primes are actually involved in this expression also. So there is no question of this product being non-convergent. Okay, so those problems are not present. Now next what we do, we are going to split this product into two parts by defining two sets. Let x be the set of those primes for which mu p minus nu p is non-negative. That means for which mu p is greater than or equal to nu p. And y is the complement of x in the set of all primes. That is, y consists of those primes p such that mu p is less than mu p, that this difference is negative. Then of course we can split this sum into two parts. So x now becomes k times that same thing, the terms remain same, but now p varies over x in this part and p varies over y in this part. Note one more thing, that the sets x and y form a partition of the set of all primes. So their union is the set of all primes and their intersection is the empty set. They are disjoint. That is why we are able to split the product into these two parts. Now watch carefully. What is happening here? For this type of primes, mu p minus nu p is greater than or equal to 0. And what was our gamma p? Gamma p was the maximum of mu p minus nu p and 0. And that is why for this type of primes, this is equal to gamma p. Okay? And this part remains as it is, p to the power mu p minus nu p, as p varies over y. Or, now from this we are going to get something else. So next what we do, we simply divide both sides by this second product. So all the exponents here will change sign. Mu p minus nu p will turn into nu p minus nu p. So x times this one, not exactly this one, but the reciprocal of this is equal to k times this. That is k times this. Okay. So this has gone to that side and now looks like this. So x times that is equal to k times this. Now if you look carefully, instead of x, we can actually consider all p's here. Even then, this product will be equal to this product y. What are the extra p's that we are considering in this product than what we have here? Namely those p's that belong to y, the set y. What happens for the p's that we have in y? For them, mu p is less than nu p. Let me write these things down. Say if you have, let me write it as a rough work here. If you have p belonging to y, then mu p minus nu p is less than 0. So what is the definition of gamma p? Gamma p by definition is the maximum of mu p minus nu p and 0. For this type of primes, that maximum is 0, which means that if we are additionally considering those primes also here which come from y, for those primes the exponents are 0. So that is why this product is in fact equal to this product. Note one more thing. You see this product, because p belongs to y, this is negative, but that is why nu p minus mu p is positive. So whatever we didn't know here, actually, this is not an integer. It's a fraction. And we do not care about the fact that it's a fraction here at this stage of the calculation. But now, when we transfer this to this side, because of these inequalities and because p is varying over by, this product is now an integer. Now whatever we are looking at are all integers. X is an integer, this product is an integer, k is already an integer, and this is also of course an integer. What guarantees the fact that gamma p is not negative? Well, that is because gamma p by definition is the maximum of an integer and 0. So in the very least case, it will be 0, but it won't be negative. Okay, so that's why in fact gamma p was defined like that. But now if you go back to your definition of q, this is equal to kq. Now what are we going to get from this? Let's see. Next we concentrate on this fact. The fact that this integer, this product, is relatively prime to this product. Their greatest common divisor is 1. But why? Well, that is because they consist of distinct sets of primes. Whatever primes that we have in y, they are not there in x. That is why I said back there that x and y are disjoint. So you have some primes here and you have some other primes here. Obviously there is no common positive divisor other than 1, and because this GCD is 1, so you see, you just try to understand this equation. An integer times some other integer is equal to some integer times some other integer. So from this equation, what do you see? You see that this product divides the right hand side. But because it has nothing to do with this thing, when we are talking about division, because of this product actually has to divide k due to Euclid's lemma from number theory. So that's how this product on the left hand side divides k. So what does that mean? Actually this other part which this product is not touching in this division, the product is not affecting this thing, and that is q. So if I now divide both sides of this equation by this product, then k divided by this will be an integer because of this divisibility. or in other words, x will be a multiple of q. Let's write that so that it becomes absolutely clear. So doing that thing, we get this. X equals k divided by that product, and this is an integer due to this divisibility, times q. So x now becomes a multiple of q, but then x belongs to the principal ideal generated by q. Recall that x was any arbitrary element in the ideal quotient I colon j. So that way, that ideal quotient is contained in q. Okay, so we write that containment that we proved just now. This ideal quotient is contained in this principal ideal generated by q. Now next we go for the reverse containment. So for that we consider this product qn, and then we write the prime factorizations of q and n. This one has the exponents gamma p and this one has the exponents nu p, and both the products vary over the entire set of primes. And then we can combine them using the rules of exponents. And again, I am reminding you that we do not have to worry about the product being an infinite product, strictly speaking, because ultimately only finitely many primes are involved. Next, we split this product into two parts based on our sets x and y. Now, what will happen to these individual products? Let's see. For the products, for the primes p of this type, which are coming from x, mu p is greater than or equal to nu p, and gamma p by definition is the maximum of mu p minus nu p and 0. Because now mu p minus nu p is greater than or equal to 0, so that maximum is mu p minus nu p. So that minus nu p and plus nu p, they cancel out, leaving us with mu p. Okay, so that is why this reduces to this. For the primes p that belong to y, the definition of gamma p is same, but now mu p is less than nu p. So mu p minus nu p is negative, and that is why the maximum between 0 and mu p minus nu p this time is 0, because the other number is negative. So for this type of primes, gamma p is equal to 0, it vanishes, leaving us with nu p. In the next line, we decide to make this product full by including also those primes that belong to the set y, besides the primes that we have here, that is those which are in x. And the terms will be this, p to the power mu p. So we are also including p to the power mu p even for those p that belong to y. But then to adjust that thing, we have to also divide by those prime powers, and that adjustment has been pushed to this product. So here, besides having p to the power nu p, okay, we are also having divided by those p to the power mu p where p varies over y. Because these two things are products where p varies over y, so we have been able to combine them in this way. And notice one more nice thing. For the primes p in y, mu p is less than nu p. So these exponents are positive integers here. Okay, they are not negative. That means this product is an integer, and this by definition is m. So that way you get the fact that qn is an integer multiple of n, or qn belongs to the principal ideal generated by m, that is ideal I. So qn belongs to I. But if qn belongs to I, because I is an ideal, if you multiply qn by any integer, that product will also belong to I. However, any multiple of qn is of the form q times k times n, where k is any integer. But k times n, that product alone is a general element of the ideal j, because j is generated by n. So that way qj becomes a subset of I. But when you have this containment, by the definition of ideal quotient, Q is an element in this ideal quotient. But if Q is an element in this ideal quotient and the fact that this is an ideal then implies that any multiple of Q will also belong to this, but the multiples of Q by integers are precisely the elements of this principal ideal. So that way this is also contained in this, and combining this containment with the previous one, you get equality. That way we have established this claim. Next, there are some exercises involving ideal quotient and product of ideals. Let's solve a few of them. I mean, we haven't completed the section. There are other things, many things are there besides these things, but some exercises are there besides the actual ones. So let's see what they are. There are some parts, but it has been named exercise 112. So the first one is this: the ideal I itself is contained in the ideal quotient I colon j, and this is very easy in fact. So let's take any element I in I. Now for any element j in j, ij belongs to I because we are multiplying this ideal element I by some element in the ring. Oh, and I must also mention that these I and j are arbitrary ideals in some ring. Okay, these are not these ij's. But then what does this mean? It means that the product of I and the ideal j, ij, is contained in I. And that is why by the definition of this ideal quotient, the element I will belong to it. So any element in I is here, and that is why I is a subset of this. In part 2 we have this product of two ideals. The first ideal itself is the ideal quotient of I and j, and the second ideal is j, and this product is contained in I. This is what we have to prove. So what we do, we take any element in this ideal and any element in j. Let x be an element in the ideal quotient and y be any element in j. Now this being in I colon j itself means that xj is contained in I by the definition of this. And that is why, because xj is contained in I and y is an element of j, so this product xy by its very form is an element in xj, and because of this containment it will now belong to I. So what are we getting? We have been able to show that the product of any element of the first ideal and any element of the second ideal is in I. But what are these products? These products are generators of this product ideal, in the sense that the elements in this product ideal are finite sums of products like that. So if these generators belong to I, so obviously their finite sums also will belong to I, and that way we get this containment. Let's see another one, the third one. This third one is more complicated because it involves three ideals, I, j and k. Not necessarily distinct, they may be the same. So we have to prove that the ideal quotient of I colon j and k is equal to the ideal quotient of I and jk, and this is equal to the ideal quotient of I colon k and j. Okay, so this is like a nested ideal quotient, and this is an ordinary ideal quotient. So what we did, we took any arbitrary element x here. So by the definition of this, xk will be contained in this first ideal, which itself is an ideal quotient. And that is why, because this is contained in this, so for every k belonging to k, xkj will be contained in I. Why? Well, xk will be an element of xk. So because of this containment, this element xk will belong to this ideal quotient. So by the definition of this ideal quotient, xk times j will be contained in I. And that is why if we take a number of j's in the ideal j and an equal number of k's from the ideal k and then consider this product, x times j1 k1 plus j2 k2 like that up to jn kn, then by the left distributive law, its extended form, you get this. But because elements like this, this is not an element, but if you take an element from j and multiply that with x and k, we do not have to worry about the order because we are only considering commutative rings. So xkj is the same as xjk. These individual terms in this sum all belong to I because of this fact. So this type of sums also will belong to I, and that is why x times this belongs to I. However, if you look at this sum only carefully, leaving out the x, this is precisely how the elements of the ideal jk look. So x times any element of jk is an element of I. So the set x times jk is contained in I. But then by the definition of ideal quotient, x belongs to the ideal quotient of I and jk. So that way any element here is also here, and that is why this is a subset of this. Now we will go for the reverse inclusion. To prove the reverse inclusion, we take any element y in I colon jk. Then by the definition of this, y times jk is contained in I, but you can also write kj in place of jk because product of ideals is a commutative operation. And that is why for any element k in k, because of this containment, yk times the ideal j is contained in I. But then by the definition of ideal quotient, the element yk belongs to the ideal quotient I colon j. But this is happening for every k belonging to k. So the set y times the ideal k is contained in this ideal quotient. But then again by the definition of this ideal quotient, y belongs to I colon j colon k. So that way any element here is also here. So this is a subset of this. Now we have both the inclusions, so we can conclude equality. So equality. And finally, if we consider this, that is this one, and use the fact again that in place of jk we can write kj. So we can then apply whatever we proved just now to this. Then this will be the ideal quotient of the ideal quotient of I and k and j. You can view this third identity, or you can say identities, as a way of simplifying these nested ideal quotients like this. You take the product of the adjacent ideals, and using this you can now handle any longer nested sequence of this ideal quotient. You get my point. There are other parts also, we will see them in the next video. And tomorrow I think we have calculus. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.